All right, hey folks. Okay, so picking up where the last video left off, right? You're trying to choose what properties you want in your telescope because all telescopes essentially work the same way, and yet every telescope in the world is slightly different because they have a different job in mind. Different telescopes are built with different tasks in mind, different mysteries they want to solve. And so all of those details about what kind of telescope, what kind of focal lengths and diameters, right? Those properties that we talked about last time, those are the first step, right? Those are the most important things. What kind of magnification and field of view do you want? What kind of light gathering power and resolution do you need? Those are the big ones, right? But the job's not totally over yet. There's a few more choices that you want to make sure that your telescope will do what you want it to do. So, um, some of the other choices that you want to make are how do you want to mount the telescope, and what kind of detector do you want to attach to the telescope. So, what's the mount, right? The mount on a telescope is basically all of the infrastructure, all of the parts that hold up the telescope and allow it to move to look at different parts of the sky. So there's two main ways to mount a telescope, right? So sort of like I was saying, right? Here's the arms that are attached to the telescope. Here's a little rotating gimbal that moves the telescope. Here's the tripod holding it up if your telescope mount has a tripod, right? But basically all this is the mount, right? And there are two ways of mounting a telescope, generally speaking, right? An alt-az mount or an equatorial mount. So the one on the left here, right? This is an alt-az mount, meaning when you tilt the telescope up and down, then you're looking up and down. You're looking at different altitudes, right? When the telescope rotates left to right, then you're looking left or right around the horizon, so the telescope is moving in azimuth, right? So essentially an alt-az mount is like a cannon, right? The telescope just moves up, down, left, right, and that way you're pointing at a point in the sky in altitude and azimuth, right? Nice, simple, easy to use, less expensive, great. The other way is where you mount your telescope at an angle, right? So notice there's this wedge here that is tilting the telescope backwards. Why would you do that? Well, because if you tilt the telescope backwards so that the rotation axis of the telescope lines up with the north celestial pole, then if your telescope is lined up with the North Pole, then essentially your telescope is lined up with the Earth, right? With the North Pole and the equator. And so when your telescope tilts up and down, it's not just going up and down, it's moving north or south. It's looking at different declinations. And when your telescope rotates left to right, it's not just going left to right, it's going east to west, right? So that equatorial mount means that the telescope moves in the equatorial coordinate system. Up, down, left, right becomes north, south, east, or west. Right, why would you pick one or the other? Well, that affects how the telescope is mounted, affects how the telescope can move, right? When your telescope is alt-az mounted, the telescope can only move up, down, left, or right. Well, that's not how the sky moves, right? So imagine here, I've got my little diagram. Here's the horizon. Here you're looking due south, and then east is off to this way, and west is off on the right. And so how does the sky move, right? The sky rotates, or, it's the Earth that's really rotating, but above our head, it looks like the sky is rotating east to west, right? Things rise in the east, they cross high in the southern sky, and they set in the west. So the whole sky is rotating east to west, so westward, but that's not how your telescope moves if it's mounted alt-az, right? So if you're trying to watch an object over the course of one night, then your alt-az mounted telescope is kind of herky-jerky, right? That star is moving, up and from the east through the south and into the west, but your telescope can just move up, right, up, right, up, right, up, right, da, 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 da. And so to track an object, to follow an object and watch it all night long is pretty inelegant. It's pretty jerky, right? But like I said, it's easy to move the telescope when it's Altaz mounted, right? You just move the telescope up and down, left and right. But then watching something all night long becomes kind of a pain, right? But if your telescope is equatorially mounted, now, I mean, this is more expensive, and also you've got to be really sure that your telescope is aligned so that the axis is pointing at the North Pole. But if you do that extra, if you spend that extra money to mount the telescope on the wedge, if you do the calibration to make sure that the telescope is pointing at the North Pole, then your telescope can move nice and smoothly and easily. Because if you point your telescope at a star or at some object that's rising in the east, as that point on the sky goes overhead from east to west, that's how the telescope moves, right? The telescope moves east to west right along with whatever you're looking at in the sky. So watching something all night long becomes really easy because all you got to do is point your telescope at that object at the beginning of the night, and then slowly but surely over the course of the evening, you just have to move the telescope westward, right? Rotate your telescope to the right, westward, and then you can track that object all night long without having to make jerky corrections. So an equatorially mounted telescope is more complicated, more expensive, but it's a lot more elegant to run. It's much easier to run once you got everything set up. Well, I said a second ago, right? If you rotate your telescope slowly over the course of the night, then you can track an object. So what do I mean by tracking an object? What I mean is you just point your telescope at an object and the telescope stays pointing at that object, tracking it overhead all night long. And you don't have to do that manually. You've got motors that can do that for you, right? Any equatorially mounted telescope should also have a tracking motor. And so when you turn that tracking motor on, the tracking motor rotates your telescope westward at a rate of 360 degrees per 24 hours. So basically, your telescope with the tracking motor on, you point your telescope, you point your equatorially mounted telescope at an object at the beginning of the night, and then you turn on that motor, and the motor does all the work for you, right? The motor rotates the telescope at the exact same rate that the sky rotates overhead, and that way, whatever you're looking at is right in the middle of your field of view. The telescope stays pointing right at that object all night long, right? Why would you do that? Well, because with a tracking, if your telescope is tracking, then you can take really long exposure photographs, right? What is a long exposure, right? A long exposure is where you open up the camera and you point your telescope and the camera just soaks up light over an extended period of time. So, for example, here's a shorter exposure, right? Here's an image that was taken in less time. And if the telescope and if the camera soaked up light for less time, then you can really only make out the really bright things, right? Here's the bright center of this star cluster. Here's a few really bright stars here. And all the really faint stuff doesn't really show up very well. Well, if your telescope can track, then you point the telescope at that object, turn the motor on, and this object stays smack dab in the middle of your field of view all night long. And if the object doesn't move across your image, then you can just soak up light for minutes, hours, as long as you want. And the longer you soak up the light, everything looks brighter. The bright things look brighter, right? The bright center of this cluster looks brighter. These bright stars look brighter. But also now, all the faint things look brighter. So now you can find the faint stars in this cluster. You can make out all the faint details. You can only take a long exposure if your object tracks, because if your telescope is alt-az mounted, you're constantly having to move the telescope which means your telescope is not always aligned. It's not always pointing at the same object in order to take those long exposure photos. So an equatorial mount is more work and more expense, but it also allows you to take longer photos, take longer exposure photos, and see deeper, fainter objects in the universe. So that's why we bother doing it. Right? Okay, so those are the two mounts, right? Equatorial mounting, alt-az mounting. One is better at pointing the telescope, and one's cheaper. Pick the battle you want to fight. The detector is the device that you are shining the light into on the telescope. The telescope collects the light. The telescope mirror or lens focuses the light, and then you shine the light where you want it. Right? Shine the image where you want. Shine the image into the detector that absorbs the light to see what the sky looks like. So in the last video, we were using the naked eye, right? You've got your eye, the image comes shining out of the eyepiece into your eye. The lens in your eye focuses the light, and so that image that shines out of the eyepiece of the telescope gets focused onto the back of your eyeball, onto the retina, and then the cells in your retina absorb the light and communicate through the optic nerve, communicate to your brain what you see, right? The very first detector that telescopes were used with was the eye, because there was no way to record light back then. You would just point the telescope, shine the image into your eye, and you'd see what the telescope saw, right? Which is nice for when you want to see things for yourself, right? See what the telescope sees. But the downside is you've got no ability to save the image. As soon as the light goes in your eye, it gets absorbed by the cells in your eye, and it's gone. By the way, the cells in your eye that absorb the light are called the rod and the cone cells. The rod cells are essentially, they're for seeing black and white. They're for seeing dim colors, or dim sources of light. The cone cells are the cells that detect color in the retina of your eye. This will come back in a second. But instead of shining the image from the telescope into your eye, you could shine it onto these other detectors also, these other devices that can actually record the image or record the data, and then you can analyze it later. So, the eye was the first one, but one of the other things that we can do these days is use a CCD camera. All right, now this takes a little bit of explaining. So a CCD stands for a charge-coupled device. Basically, it's an electronic device for taking pictures, right? The reason why it's called a charge-coupled device is that it takes in the light and then couples that to electric charges, basically electrons, right? It takes in light and spits out electrons, and then your computer chip reads off those electrons. Here's how this works. Let me break this down, because you need to sort of understand this to understand why we take the pictures that we take. Okay, so the CCD, this device, this computer chip, has this sensor layer, right? So light comes in, right? Photons, what's a photon? A photon is a particle of light, right? The photons come in from the telescope. The telescope takes in the light, focuses the light, shines that light, and instead of the image from the telescope shining into your eye, it shines onto this CCD sensor, right? So the light comes in. Well, each of these photons, each of these particles of light that hits the sensor knocks loose an electron. So the energy from this photon knocks an electron out of its atom in the sensor, and that electron gets knocked out over here, and as the sensor absorbs more and more electrons are knocked out, and they're collected in this well. All right? So you do this, you let the light shine onto the sensor, knock some electrons out, and the electrons the electrons accumulate for a few seconds, a few minutes, however long you want. And then eventually you tell the computer, okay, pull the electrons out of the well and count out how many electrons there were in the well. The more electrons were in that well, the brighter the light that shined on it. Right? But what I have here only measures brightness, right? Light comes in, electrons go out. The more electrons the computer counted, the more light must have hit the sensor. This is not really taking a picture, right? This is just a sensor that measures brightness. So how do I take a picture? How is this a camera? Well, you don't use one sensor. You use a whole array. You use rows and columns of these CCD sensors. And so this is basically the camera. This is the CCD is essentially the film in a digital camera. Every digital camera you've ever used, the one, if you're a photographer and you shoot images in digital, or the camera on your phone or your laptop, every digital camera has this array of CCD sensors that absorb the light and save the image, right? So here's how it works, right? You open up the camera, right? You point your telescope at an object, you open up the camera, and the light shines, the light gets focused by the telescope, and it shines onto the CCD. And so let's say the light shines right there, right? When I shine my image onto that CCD, there's no light here, right? The sky is dark here, but there's some light here that shines on the sensor. There's some light here. There's some light over here, and that's it, right? These areas of the sky over here where no light is shining, well, that area of the sky must be dark, all right? And so you let the camera soak up the light for a few seconds or a few minutes, and then after you're done soaking up the light, then the computer pulls the electrons off of those sensors and counts up. Okay, how many electrons are here? 0. How many electrons are here? 0, 0, 0, 0, 0. And then, eventually it comes to, okay, there's light here, but there's no light over here. There's light here, but not here, 0, 0. 10 photons, 20 photons, 0, 0, 0. 20 photons, 10 photons, 0, 0, 0, right? So when the computer reads off those electrons, it basically creates a spreadsheet of rows and columns of numbers. How many electrons did it count in each pixel of the sensor? And then if you're running this computer, you take the computer file that says how bright each pixel is, and then you turn that back into a picture on your screen, right? In the pixel on the image where it was dark, where there was no electrons, make that black, right? Where there was lots of electrons, make it white. If there's a smaller number of electrons in the middle, make it shades of gray. And so you take that file on the computer that's just rows and columns of numbers, represent it as shades of gray on the computer, and the computer shows you that, and you go, oh, it's a smiley face. All right? A CCD camera is a map of how bright these different areas on the sky were. Was there no electrons? Was there lots of electrons where it's bright? Or is it somewhere in the middle? Right? And this is the thing about a digital camera. A digital camera only shoots images in grayscale. It's all black and white in shades of gray, because all the CCD is doing is taking the light in, spitting out electrons, and saying, how bright is it? Is it bright white? Is it dark black? Or is it some shade of gray in the middle? And so you say, but wait, I've used a digital camera with my phone or whatever. It takes a color picture. How does this CCD take a color picture? Well, For that, you need filters, right? So every color camera, every color digital camera has filters that filter out the light. So let's say this one's got a filter with 3 colors, right? This red filter only lets through red light. So this light source, this object that you're pointing your telescope at, shines into the filter. The filter only lets through the red light, and that's what hits the CCD. So now the CCD has a map of how bright is the sky in the red light. And then you rotate the filter wheel, rotate that filter so that now the green filter is in front of the CCD. And then you take another picture that's a map of how bright is the sky in the green light. And then you rotate it again so that the blue filter is in front of the CCD. You take a third picture that says what's bright and what's dark in the blue light. And then you layer those 3 images on top of each other to get a full color image. So, for example, the example out of the book that I'm going to reuse here, right, is like, let's say I'm taking a photo, of my neighborhood. But if I want to take a full color image so that it looks true to the human eye, I have to take 3 pictures. A picture in the red light, the green light, and the blue light. So I take a picture in my neighborhood with a red filter. And in the red filter, the stop sign's really bright, the sky's pretty bright, but this tree thing over here, well, that's dark. And then I take another picture in the green light with the green filter. Oh, all of a sudden this stoplight is really dark in the green light. There must not be a lot of green light here. But there's a lot of green light over here with this tree, and there's also a fair amount of green light from the sky. And then I take a picture with the blue filter. With the blue filter, the stop sign's dark, the tree is dark, the sky is bright. So then I stack those 3 photos on top of each other. I layer those 3 images together, and what I get is a map of, okay, it's brighter in the red over here, brighter in the green over here, brighter in the blue over here. Now I've created an image that looks true to the human eye. Why do I need to take those 3 photos in order to make an image that looks true to the human eye? And that goes back to what I said a minute ago about the rod and the cone cells, right? In your eye, the cells that see color, the cone cells, they only see red light, green light, and blue light, right? The cells in your eye only pick up red light, green light, and blue light, and all of the other colors of the rainbow are just mixtures of those 3 primary colors. So if you want to take an image with a digital camera, with a CCD camera, that looks the way the eye sees, you take an image in the red light, the blue light, the green light, you stack those together, and you've created an image that shines into your eye, and it looks real to the human eye, because the eye only sees those colors anyway. Right? So a CCD camera by itself just takes a black and white photo. But then with a set of filters, that's when you can take a photo or an astronomical image with color showing up. All right? Okay, so that's the CCD camera, right? CCD camera basically means a digital camera. Or you could do something totally different, right? Instead of the light from the telescope shining into your eye or shining onto a camera, you can take the light, where's my mouse? There it is, right? Take the light from the telescope, shine that light through a prism, and when you shine light through a prism, it breaks the light up into the rainbow. So instead of taking an image of the light from a star or a planet or anything, you can take all the light from that object, split the light up into the different colors, and then you can basically divvy up the light into all the different colors, and then you can look at the light more carefully, and you can say, well, how much red light am I getting? How much yellow light? How much yellow light? How much green light? Etc., etc. Right? So this is a completely different way of looking at the light from an object. I'm not taking a photo, I'm taking a spectrum, right? When you split the light up into the different colors, the different wavelengths of light, you're looking at the spectrum of an object. right? Splitting up the different colors so that you can look at each color individually. We'll get more into how this works later on. This is a much bigger topic that's very powerful in astronomy, but we can't talk about the whole thing today. So we'll get to this in a little bit later in the semester. But suffice to say, why would you want to look at the spectrum of an object? Well, you can figure out some things that you can't figure out from a photo. Like the spectrum of an object can tell you its temperature, or what it's made of, its composition, or how fast it's moving, or what the structure of the object is. All of these things, it's very cool, which is why we'll talk about it later. All of these things that you can figure out about an object just based on the different colors in the spectrum, right? So that device that looks at the spectrum of an object is called the spectrometer. All right. And then the last thing is a timing device. A timing device, here now we're using that simple CCD where it's just a 1-pixel camera. Basically, if you have a CCD that's just one sensor and one well, you basically have a camera that just has 1 pixel, essentially. Why would you do that? That would take terrible pictures. Sure it would, but you're not taking an image. You're just measuring brightness, right? Because photons go in, electrons go out, and instead of taking a photograph, the computer reads off those electrons from the CCD, and it just counts how many electrons did I count? What's the brightness? And the computer can do that really fast, right? Because instead of having to spend all the time downloading an entire image from the CCD camera, now the sensor just point the sensor at a star, the light from the star comes in, it hits the sensor knocks loose some electrons, the computer reads off the electrons. How bright's that star? How bright is it now? 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 Right? This timing device is really fast at just taking a quick snapshot of a star and measuring how bright does it look. And so because you can take those measurements really quickly, you can make very careful, very quick and easy plots, graphs of how the brightness of things changes over time, right? Not every star is the same brightness. Some stars get dim and then get bright, and then get dim and then get bright. And that can be really interesting, right? Why do some, the sun doesn't do that. The sun's the same brightness all the time. But some stars pulsate, they get bright and then they get dim, or some stars wobble and slosh around, and so the brightness can change. And so if you're trying to watch a star and you don't really care what the star looks like, it looks like a star. You don't care you're not taking a picture. I just want to know what's the brightness at regular intervals. Then your timing device is easy. The computer just grabs the number of electrons and it says how bright the star is. Quick. Right? So it's not good for taking pictures, but it's good for measuring how the brightness of objects changes over periods of time. That's why it's called a timing device. Okay. So those are your 4 major detectors that you can, shine the light from a telescope into, right? The telescope collects the light, focuses the image, and then shines that image where you want it. What that image shines into depends on what you want to do with it. If you want to just see what the telescope sees with your own eyes for yourself, put your eye up to the eyepiece. There you go. But if you actually want to save the image so that you have the photograph that you can analyze later, use a CCD camera. You want to measure the spectrum of the object in order to figure out temperature or composition or all the things you can do with that, use your spectrometer. And if you want to measure how the brightness of things changes over time, use a timing device. Pick the right tool for the right job. That's what all of these mounts and detectors are about. All right? So, once you've made all those decisions, what kind of telescope, what kind of focal length, what kind of diameter do I need? And then what am I going to attach the telescope to? What kind of mounting? What kind of detector? Now you've made all the decisions that you need to make to pick the right tool for the right job so that you can make the measurement, take the image, do what you need to do to make the discovery you want to make. Or just to take the pretty picture that you want to take. Whatever you're doing with your telescope. All right. I hope that cleared some things up. and how we use these different detectors to make these discoveries. That's what we're going to get into for the rest of the course. All right, so we'll see you then.